Let's see multi-level indexing idea. So far we have seen single level indexes, right? So like primary indexing, secondary indexing, everything is single level. The problem with single level sometimes is, if your file size is very large, then if you create index also, that index file will be again very large. So there will not be any difference. Example, the secondary key indexing you see. Example, this is your data which is not ordered, and let's say you are creating index on employee ID, then we can go for secondary indexing, right? Especially secondary key indexing. If I create secondary key indexing, then for every different record, or of course, every record is different with respect to employee ID field. So for every employee ID, you create a record, right? So that's why almost, your index file size is as large as your original file. Then what to do? Then to reduce this index size further, then we create index on index. So that is the concept of multi-level indexing. We create index on index, again index on index, so on until you satisfy. Otherwise, your index size is very small. That is the concept. We'll try to apply it. So let's say these are all the blocks where your data resides. Then what I am doing is I am maintaining. I already told you that. I mean, for every in the index file, you can maintain either block pointer or record pointer. It's up to you, not a problem. These two are the variations. So at this moment, let's say already we have seen how to maintain record pointer, right? This time we'll see how to maintain block pointer. So anything is fine. So 1 comma, see this is b1, right? I write 1 b1. Then later 2 comma b2. See 3 is in b3 block, 4 is in b4 block, 5 is in b5, in that way 6 is in b6, in that way I filled. So it will be huge. The reason, for every entry, for every record of your original file, you are creating one entry, then your file size will be as large as original file. So how to reduce the size this time? And what if second time if you create index, again if it is not reduced, that means your file size, again if you get this much size, not possible. The reason, first time it was not ordered, right? Second time now you are maintaining ordered file. So this is called first level index. So what is the type of first level index you are using at this, in this example? This is secondary key indexing, right? Secondary key indexing, because index on key field and data was not ordered on that key field. Now this time your index, if you see, index contains employee ID and block pointer, correct? My question is, so your index now is dash ordered file, correct? With respect to employee ID field, because our search field is employee ID, then with respect to that your data is ordered, then I can go for primary indexing this time. That is the advantage. Whenever I go for primary indexing, definitely my indexing size or index file size will be drastically reduced. We'll see that. So second level. In the second level, what I do is, for every, we know the concept, this is a file. How to create primary index? For every block, one entry, correct? So these are all also pages in your disk, right? So they will be stored in blocks. That's why I can say that this is block number 9, block number 10 and B11, just for simplicity, B12, they need not be contiguous, B13 and B14, B15 and B16. Let's add the entries in indexing file, second level. First of all, this block B9, in B9 what is the first record? 1. So in B10 what is first? 3, in that way. In B11 it is 5, right? 5 B11 and 7 B12. Then 9 would be B13 and 11 will be B14, in that way. 9, 10, 11, 12. Now 9, 10, 11, 12, 13, 14, one more. One more is 15 and 16. B15 one entry, B16. That is primary indexing. For each block one entry, we know that, right? So 11, after that 13, then 15. Now again use, right? You have 4 blocks. Still you are not satisfied. Then what you do is you go for one more level of indexing. That is primary indexing again, because see, your file is ordered and you are creating index on employee ID field. Employee ID, this is block pointer. So let's go for that. This time I assume that this block number is 17, B17. This is B18. This is B19. This is B20. So let's go for that. So this is called third level. In the third level index, we have 1. Where 1? 1 is in B17. So what is the starting record in B18? 5. 5 in B18. In that way. Next block. Where is the next block? B19. What is the starting record? It is 9. Then next one is 11, right? Sorry, 13. 13 is in B20. So in that way we go for one more level, third level. So next time we can go for fourth level, of course. In the fourth level what I do is I need only one block. In that, let's say this is B21, this is B22. I would go like this, 1 in B21 and 9 which is in B22. You understand? Now finally this is the index. So if you see the fourth level, in that there is only one block, right? So let's say this is B23. Now we say this is start, right? So we put an arrow just for imagination. Now I show some of the pointers. See, B21 is pointing to, I show like this, B21 points to this box and B22 points to this box, right? Now similarly, because of B17, so it points like this. Which box? B17. Now B18 points to this box. Now B19 points to this box and B20 points to this box. In that way we can show the pointers. Now here B9 points to, see here, B9 is here. So we have to show the pointer like this, right? So B9 points here and B10. B10 goes like this and B11. So B11 points to this box and B12 points to this box. In that way we have to show the pointers, remaining pointers. Okay, I'm not showing, but you can understand. Now what I want to say is this is multi-level indexing, and how this multi-level indexing will be accessed we'll see. First of all, example, let's say you are searching for a record called 16, G, which is the last record. Whether we reach or not, we'll see with this index. So how to access this index is, it's a tree model. Now if you see from right to left, you understand that it is actually tree, correct? So in this one 16, G, so 1 and 9 you search it, and you understand that since 16 is bigger than 9, then we have to take this pointer, B22 pointer will come here and you search here. So where is 16? Is it this one? No. Then this one? No. Since 16 is greater than 13, then take this pointer B20, come here. Now B15, we are in B15, but records are 13 and 15. So our value is 16. So take this 15th record, that means 15th corresponding record, B16. Go to B16. This is B16. Now we are our target is 16. Yes, I got it. Then what is the corresponding pointer? B8. In the first level we got pointer B8. That is actually the pointer of original record. Directly go to B8. See, and sorry, this one, right? B8. In that, so search it. Now if you search, you get it. In the place of B8, if you have record pointer, I would have directly got here, but not a matter, right? So finally we can access it. We'll see one more time. So let's search for 12. When you search for 12, again we have to start here, 1 and 9. Since 12 is less than 12 is greater than 9, take this B22, come here, search for 12, 9 and 13. See, one important property here is all this index is ordered index. That means you can apply binary search here. So using the binary search, I realized that 12 is in between 9, 13. So I use, 9's pointer. So after 9, this one, B19. So come to B19. Again search for 12. So it is 9, 11. So 12 is after 11. That's why take B14. Take B14 and search for 12. 11, 12. So yes, 12 matches, right? So that's why you take this time B6. If I take B6, I will come to this one. Then search here, 6, 12. Then here you get it, right? And you print it. Since it's a key field, so only one such record will be there, correct or not? That's why it is secondary key indexing, first level, right? So we understand this. So next one more time we'll see. Example, let's say you are searching for 5. So 1, 9. So 5 is in between 1 and 9. So take this pointer. If it is after 9, take this one. It is before 9, 1, then there is no such record. If it is in between 1 and 9, take this one. This pointer I can say in between 1 and 9. So B21, come here. So searching for 5. Yes, it matches. Then you take B18. So B18, you come here and search for 5. Then yes, B11 is the right pointer. Come here. You are searching for 5. Then B5 is the right pointer. Go to blindly B5. You get it. Yes, it's perfectly working. So this is about multi-level indexing. Now how many blocks we transfer? Otherwise, how many blocks we access to search for one record, we will see. Example, let's say you're searching for one record, then first we start here, then this block has to kept in main memory and we have to process it. So one block, and after that, because of this pointer, we'll come and we refer this block, another one, right? Otherwise, if you use this pointer, we refer this block. So what I want to say is, in this level, only one block you are accessing. Similarly, we can understand that it's a tree structure, either we go left or right. So that's why out of 4, only one block we were referring. So one more block here, and in this set we only access one block, and in the data you are going to access only one block. So I can say that in this, especially in this multi-level indexing, the number of blocks we are accessing are 1, 2, 3, 4, 5, correct? 1, 2, 3, 4. There are 4 levels of index. So that's why 4 block transfers, and in original file 1. So total 5. Is it not constant? Whatever the big file it is, it depends on only number of levels. Example, let's say in this model, if you have n levels, okay? So if you have n levels, then the total number of block transfers equal to, for every level 1 block, so n block transfers, plus in the original file 1 more. That's why I can say n plus 1. Since n value here 4, it is 4 plus 1. Understand? So sir, 5 means very big number, right? Yes, it's very big number, but here you see your file contains only 2 records in each page, correct? But generally that is not the case. In general, what happens, you will have thousands of records in one block. If that is the case, then definitely number of block transfers will be reduced, because it is again a level number, right? So the problem here is, in this example, every block is containing after all 2 records. That's why you don't see any significant difference. What we do is, we see one numerical problem which is asked in GATE about multi-level indexing. On that you can see the difference. Okay, see this GATE question which is asked in 2008, I think. Consider a file of 16,384 records that is given. Okay, remember it. So stop the video and read the question and understand it. Now each record is 32 byte long. So record size is given, and key field of size 6 bytes. We need that also. The file is ordered on non-key field. Note down. So non-key field. That means, so remember it. That means finally your file is ordered for sure, but on dash field non-key. Remember it. And the file organization is unspanned. So we know what is spanned and unspanned. Whenever it is unspanned, you know how our calculations vary. We know that, right? We will see. The file is stored in a file system with block size 1024 bytes. Remember it. Block size is 1024 bytes, and the size of block pointer is 10 bytes. Okay. So record pointer is not given anywhere. That means you can understand that. So in every index you are just storing the block pointer everywhere, right? So no record pointer is stored. I already told you how to use block pointer as address and how to use record pointer, right? Anything we can use, not a problem. If the secondary index is built on the key field, okay, so remember this point. We are creating secondary index on key field, but data is ordered on, so it is given, right? Data ordered, yes, but data is ordered on non-key field. When data is ordered on non-key field, then data might not be, otherwise most of the times and 99% of the times data cannot be ordered on key field. That's why, but we are creating index on key field. Though your data is ordered, for me it is unordered, because my target is key field. In on key field, data unordered. So next statement is, multi-level index scheme is used. Fine, I know how to apply multi-level index to store the secondary index. Okay, fine. And the number of first level and second level blocks in the multi-level index are respectively. See, finally we have to do the first level indexing and second level indexing. That means first create index. On that again we have to create index 2 times. Then the number of blocks he is asking in the first level and second level. If you see the options, so you understand that. So 1 is enough. That means if you create first level, that is sufficient. Why? So in the options, every option is differing on the first level blocks, right? If you know the answer, example, you got 256 blocks in the first level, only one option matches. If you get 128, only one option matches, right? So that's why we can decide the answer by only calculating first level index. Okay, let's do that first. After that, for completeness, I explain you how to calculate the second level. So recall how you create first level index. Especially he said first level index should be secondary index, correct? So data is unordered, remember. So this is your data. How many blocks we have, I don't know, but 16,384 records we have. Fine. Now I am just concentrating on how to create for secondary key indexing, because index is on key field that is mentioned. Then my choice is only one thing, secondary key indexing. If it is secondary key indexing, what is the idea? For every record, one entry. How many records we have? 16,384. Then in my index file, I don't know how many blocks it occupy. First of all, we'll see the file size. So in my file, my entries are like this: one entry for one record. Since there are 16,384 records, then the number of entries here would be 16,384. Finally, I got the number of records in my index file, first level. Okay, let's say it as first level. But I want number of blocks. How to compute number of blocks? So number of records into each record size. In each record, what are the attributes we are keeping? One is key field, whatever it is. Let's say it is key size, followed by block pointer. What is key size in the question? So key size in the question is 6 bytes. Okay, so your index will have 6 bytes for each record plus extra, what is that? Block pointer. What is the block pointer size? If you search, you get somewhere. Each record is 32 byte long. No. So block pointer, if you see, yes, 10 bytes long. So 6 plus 10, 16 bytes. So I want to say that my index file has 16 bytes in each record. How many such records I have is 16,384. So finally it would be 16,384 into 16. These are all bytes, right? But I want what? Number of blocks. First of all, we'll focus on block size. What is our block size in the question? 1024 bytes. Note down. What is your record size? 16 bytes. Let's try to divide it first. So when you divide it, it will be properly divisible. That means what? So your block size, so in whether it is spanned organization or unspanned organization, then effective block size is same. That means you are utilizing the total block. If you utilize total block, then how many blocks are required to store this much file? 16,384 into 16. So it's simply divided by block size. Remember one thing, simply calculate effective block size, whatever the organization is, it is, right? So finally it will be, sorry, if it is spanned organization, directly we write original block size. If it is unspanned organization, then we have to write effective block size, because we are wasting some space. We should know it. Already I taught you how to calculate effective block size. So it would be 16,384 into 16 by 1024. If I simplify it, it will be 2 power 14 into 2 power 4 by 2 power 10. It would be 2 power 18 by 2 power 10, which is nothing but 2 power 8, which is nothing but 256. I got the answer here, option C, 256. But for completeness, I will teach you how to calculate the second level answer. So let's recall. This is first level. So did you remember in my idea? Otherwise, in our multi-level indexing scheme, we created, because your first level index can be ordered. We can maintain ordered. You have to maintain ordered. Okay. So when you maintain ordered data in the first level, then next level what I can do? I can create, either primary indexing or clustered indexing. Since your index field is key field, then I can go for definitely primary indexing. Now I am going for primary indexing. If it is primary indexing, how your file looks, that means what are the entries in your primary indexing? Just recall, in primary indexing, one entry for, that is very important. If you know this concept, you can answer any question. So one entry for one block of your file, right? One block. So here, since we are creating index on this index, so for me this is main file. Forget about that one. I am not creating index directly on that. So how many blocks this index has? Let's recall. Just now we calculated. There are 256 blocks, right? Now on this 256 blocks we are creating the index. So we know that since it is primary indexing, for every block we maintain a pointer, correct? So please recall primary indexing, otherwise go through that videos again. So in primary indexing, if it is primary indexing, one entry for one block. How many blocks we have? 256. Then finally I got number of entries in this primary indexing, 256 entries, right? And one more thing, what is the entry size? Let's calculate. Entry size, if you want to know, what are the things you are keeping in primary indexing? Key field, again block pointer, right? Key field is 6, block pointer is 10, 6 plus 10, 16. Now again, since it is unspanned organization, we should see whether complete block you are using for your file or some wastage is there. So again go back to your block size 1024 bytes. So this is 1024 byte block. Now current records in this file, records are again 16, right? So that means I am not wasting the space like first level index. So same, right? So there is no wastage of space, then I can say that my effective usage is full. Now come back to our problem. What is your index file size? 256 records, correct? And each record size 16. This is your original file size. Then how many blocks are required? Simply divide by effective block size, which is 1024. It would be, so if I simplify, 2 power 8 into 2 power 4 by 2 power 10, 2 power 12 by 2 power 10, which is nothing but 2 power 2, I think, right? Which is 4. Yes. So 256 comma 4 matches the option. So finally, the correct answer is option C. Let me introduce you one more indexing technique, that is indexed sequential access method, also known as ISAM. So how this ISAM works, we will see. So let's see the idea about ISAM. So these are all the nodes in ISAM. So these are all leaf pages. Here we actually store file, your file. And these overflow pages we'll discuss before that. So these are all index blocks, otherwise index pages. Okay. So also known as, because since it is a tree, we can say these are all non-leaves, leaves, and these are all overflow pages. We'll see one by one. Like first of all, we ignore overflow pages. We see only leaf pages and this index pages, otherwise non-leaf pages. So in leaf pages, you are going to store your data, maybe like this 1, 3, something, 7, 9, 16, 24, along with its complete data, right? So example here, I put star mark. Star means the remaining data. Like example, these are all employee information. Student, employee ID 1 followed by employee name, salary, everything. That is star. 3 star. 3 is a key and star means remaining information. In that way, your file will be stored. Okay. So just because I don't have space, I am keeping star. In that way, this is your file. Now in this next level, you will have, other keys, like, just keys. Maybe example, here you might have 7. So this 7 says that, and one more key you will have, because there are 3 pointers, right? So we will maintain 2 keys here. So one is 7, one is 16. So all the elements which are less than or equal to 7 will go this side. All the elements which are greater than or equal to 7 will come in between 7 to 16. All the elements which are greater than or equal to 16 will come this side. This is the way this index works. Similarly here, example, this value is 25 something, and let's say you have here 30 and 40, 50, okay, 70, 90, along with that information, remaining information, let's say star. So when you have this kind of all data, so I can say this is your after file. Okay. So here I maintain some values so that this should be properly indexed. That means, so here I keep 2 values. They are, one is 40, second one 70. Now 40 is left, you have a pointer which is going to point all the records whose key values are less than or equal to 40, and this pointer is going to record or store all the values which are greater than or equal to 40. Here all the values which are greater than or equal to 70. So but how to create it? So whenever you have a file, usually, so this thing will happen. This is your file. Once you have a file, then we create this level of nodes. I will show you how to create this level of nodes. Remember one thing, this is actually static indexing technique. That means, so this one, initially you have a file first of all. For that file, we create these nodes. After that, we will extend this, and next level nodes we create. After that, we link these nodes to next level. In that way, systematically your tree will be constructed in a static mode. Okay. So I will show you clearly how to create this tree. Sir, I have a question. One imaginary student asked this question. What is that? Sir, it's fine. So I understand. Example, let's say I'm searching for something 17. Then I come to this point somehow, because I start here. It's a search tree. Since it is a search tree, these keys will help you for indexing. So since you don't have complete tree, but you can understand that somehow will come here, and example, once I come here, I can really fetch the record. Example, I am searching for 16. I am here. Then I search in this node 7, 16. Yes, I take 16. I come this side and I fetch the record. Yes, it's possible. But sir, suddenly if new records comes into your file, so whenever new record comes, then we don't extend it. That's why it is, this process is static indexing. So whenever a new record comes, like let's say something called 55. So what we do is, first of all we search for 55. So 40, 70, 55 will be in between, right? So we'll come here. So after that, here we search in this leaf, do you have any record like 55? No, then we insert. So we insert it in overflow page. So in that way. So this overflow page is created dynamically when you are creating new nodes, otherwise when you are inserting new nodes. Example, whenever you wanted to create a new node, like let's say value 55 and its information 55 star, that means total record, then 50's right will be linked like this. I can link like this. Okay, sir, if 57 comes, so in this overflow page, I add one more entry 57. So these are all might be ordered, might not be. You can implement anyway. So 59 we keep here. Example, let's say one more element comes. Example, here you have 95 comma 100. If 105 comes, probably then maybe your search ends here, but you don't get, let's say 105, then we create a new entry in the overflow page. In that way, overflow pages will be useful, but we never add data to your leaf pages, and leaf pages are always fixed and they will be decided by number of records in your file. So initially whatever the file you have, based on that I fix this tree. That's why it is static tree. So this is going to be, so your tree will not be extended, otherwise your tree is not going to be grown up. That means it is not growing or not shrinking, neither growing nor shrinking. Only overflow pages will be added. So in that sense it will be growing, but apart from that nothing will be added. So if you understand this one, then we say that this is so ISAM. Now, sir, you did not discuss deletions. How deletions will take place in this tree? In this tree, deletions will take place like this. Example, you are deleting a value which belongs to overflow page. Then simply we delete. We are happy. And one more deletion. And one more deletion in that way. Example, let's say if you delete some data such a way that your entire page, overflow page, is empty, then we delete this overflow page. That is the way overflow pages are removed and added. Again 55 comes, I create a overflow page and I add 55. Then 56, everything will sit here in that way. So appropriate overflow page will be updated. Now, sir, what if I want to delete 70? Is it possible? Yes, because whenever you want to delete 70, we have to delete it. We can't maintain it in the leaf page. Then only, but we don't update anything. Simply we put a mark like this. That means 70 is deleted. Now, sir, if 90 is deleted, yes, it will be deleted. But you know, this page will be completely empty, but it will not be modified and nothing will be added at this moment. Sir, why you are not at all deleting this page? Overflow page you deleted, right? That means overflow block is deleted. Why you are not deleting this page? So already I told you in this ISAM method, the leaf pages are fixed. They will not be deleted. The new pages will not be added to the leaf pages. They are fixed. Okay. So if this kind of situation happens where all the records in one leaf page are deleted, we maintain the empty page. And next time when new insertion comes, then we add here. So these empty pages will be used for the next insertions. I can say it is a reserved space. Understand? Now delete 40. Simply delete it and put a mark like this. That means this 40 record is deleted. Delete 50. Simply delete 50 and put a mark that 50 is deleted. Now again insert 40. So because of your search process, definitely you will come for here and we add here. Insert 50, you add here. Insert 55, search for 55. If while searching for 55, definitely you will come here. Then since there is no space and there is no 55, then we add in the overflow page. That is the concept of ISAM. Understand? So now we'll see with one example, like I take some data and I'll try to create such kind of tree. Okay. Now we'll see how this ISAM tree will be created. Okay. So this is your original file. So I hope you understand what is star. Star means remaining information about every record. So 10 is an example, employee ID 10. Then star means employee name information, salary, age, everything. So rather than writing, because I don't have enough space, right? So I'm writing star. 15 star, 20 star means I can imagine it as a record. So this is complete a record. So in that way. Now when you have this kind of file, then we are going to create ISAM index. How I create ISAM index is, first of all I take a block, okay. So in the next level, that means I am going to complete the next level. So in the next level, you will be having one page or block. I assume that, let's say, this block capacity, we will see how block capacity can be calculated. So this block capacity at this moment is only 2 keys. So if you can hold only 2 keys, then what I do is I keep the second node and third node's keys and starting values like 20 comma 33. Slowly you understand why I am keeping exactly this 20 and 33. So here this rectangle box is, I mean, I'm just using to show that it is a pointer. Okay. So here this pointer is going to point to this node. We have block 1, block 2, block 3, so on. Let's say, then here we are going to write block 1. Now here I am going to write, because I want to keep a pointer here such a way that it will point to all the files whose key values are in between 20 to 33. That's why this one. Now here I write a pointer which is going to point all the key values whose values greater than or equal to 33. So that's why this one, right? Now similarly for these 3 nodes, I create one more node. So this is fixed structure. So it's fixed like this. So I assume that again in this block only 2 keys I can accommodate. If that is the case, then I use here 51 and 63. So 63 is next is here, and in between 51 to 63 here, and 51's left is here. Now I will create a next level node like this. Now again here also same, I mean every block size is same, correct? Then here my assumption is this page also can accommodate 2 keys, but we don't require 2 keys, right? One is enough. So in this structure, because I have only 2 nodes, then I use only one key. Okay. So let me fix here or here, doesn't matter. Let me fix that key value as 40. You understand why it is 40. See, these are all nodes pointed by this node, and these are all nodes pointed by this node. Now see your value, if you see logically, so we are going to have a tree structure. So there is a pointer here and there is a pointer here. Try to understand. Okay, this is empty space. Now why it is 40? Because otherwise you can keep 37 also. So if you keep 37, so that number should be such a way that all these values should be less than or equal to 37, correct? Less than 37, correct? That is what we are following. Right side values are greater than or equal to key value. Since 20, see 20 greater than or equal to 20, correct? Here these values are all less than 20. Similarly, if you follow that, so 37 will not work, because if I keep 37, so my idea is all these values should be greater than or equal to 37, but that this 37 is at left side. That's why 37 will not work. What if I keep 40? It will work. You see, all these key values are less than 40. Absolutely right. All these key values are greater than or equal to 40. Perfectly right. So 40 is the right value with my logic. So this is the key. So this part you can ignore, of course, because storage wise there is a space, but tree wise, if you see logical tree, it will be like this: 40, 40's left is this node, 40's right is this node. Now this is called ISAM tree. Okay. So initially it is a static tree. It will not grow dynamically. Only overflow pages will be growing. Otherwise remaining thing is same. We never increase the number of leaves. These are all called leaves now. That is what I said. Okay. So this is leaf, where you keep the data pages, right? So this I can say non-leaves are all index pages. Now we have also overflow pages. When you overflow pages occurs, I will tell you. Now you try to insert a value called 35. Example, whenever you want to insert 35, search for it. If it is there, first, why we search actually is to find out the location where we have to keep it. Usually in the leaf, that means in the last level, we have to keep the values. So start, that you remember it. In any tree, usually in data structures also I taught, in binary search tree or in binary tree, usually we insert at the leaves, right? So similarly, search for, first of all, 35, you identify that, 40, go left, 33, right? So we have to search this entire node. When you search it, you realize that 35 is after 33. So take this pointer, you come here and search for it. Do you get it? No. Then you reached already leaf, right? You can identify that. Whenever you reach leaf, then stop it, you did not get the 35 value, then we create a new record in the overflow page. This is the time we have to create overflow page. So some people think that, sir, why don't you keep 35 here and move this one here, move this one here? So it's time taking, right? You can understand. So many movements will take place. To avoid that, we actually create overflow pages. My assumption is rarely we do insertions and rarely we do deletions. In that case, usually this HiSam tree will work perfectly. So now see 33, 37. Just this node will have only one pointer that points to this overflow page. Okay, so don't say that, sir, is it not after, I mean, why it is after 37? It's not after 37, it is after this node. So whatever comes after this node, it will fit here. Okay, example 36. Again I keep 36 record in this page. So if this page is full and if 34 comes, search for 34 first, go left, 33, go right, then you come here. Is there any 34 record? No, then we have to insert, but there is no space, let's say. Then create a new block or new page, both are same. So keep 34 along with its all the record. So this entire record, then link here to here. In that way, overflow pages grows, right? In the worst case, you will have a lot of overflow pages. That's not good thing for us, correct? But usually our assumption is insertions and deletions are very rare, then only go for it. So of course you can see the disadvantage easily, that it is not dynamically growing and shrinking, correct? So it's a static data structure. And so when in the worst case, if there are lot of insertions, because of that you will be having lot of overflow pages. When there are lot of overflow pages, it will take lot of time to search. Example, you are searching, imagine that there are lot of overflow pages, for one node, one leaf. Then you are searching for something here, something called, let's say, x. When you are searching for x, come here up to this fine, then we come here up to this fine. So we are indexing through tree, then usually it takes very less time. We will see soon why tree usually takes very less time. In whoever studied data structures algorithms, you might have known that, because in binary search tree or in any balanced tree, quickly we can search the data. So far here it is good, but after that this is linked list. So it takes lot of time, because this block we have to search, this block, this block, this block, so many blocks. That's why usually linked list structure is not good for especially for our problem, correct? So each linked list, if if I traverse each linked list node, that will be one disk transfer. We have to reduce the disk transfers, correct? That's why there is a problem with overflow pages. How to avoid it? We have an alternative tree structure, that is B plus tree and B tree. So we are going to study, that's why B trees and B plus trees, which are dynamically growing and shrinking data structures, which are going to overcome this problem, right? So we'll see that. Before that, we'll see one gate question related to this ISAM tree. Okay.